make yourself scarce. Hello and welcome to another wonderful adventure of the New York City Category Theory Seminar. Tonight we have Alex Sorokin from Lviv, Ukraine, believe it or not, and he's going to talk about the defect of a profunctor. Take it away, Alex. Oh, Alex, you're on mute. You're on mute.
Again, thank you so much. Now I'm unmuted, and I will go slowly but with a good pace through many things. So my topic has my talk is divided in 6 parts.
One second, Alex. You gotta give the introduction of the 4 things. You're on tape now. Where you were born.
Okay. Since we are on tape, so I am right now located in the city of Lviv in Ukraine. In the same city I was born, in the same city I got my first undergraduate degree. In this city I get my first serious degree. In this city, what else did? I did many other things. I'm finishing PhD program at Northeastern University in Boston, USA, and I already got a job. What job? It's another question.
Perfect. Go ahead. Talk about. I like the fact that you said you're talking slow. I like that. As slow as you can. This is all. Don't assume you know anything. Go ahead.
Okay. So my talk is divided in 6 parts, and 3 of them, second, third, and fourth, will be introduction to quite well-known subjects in category theory for people who work with them. But of course, I will start from the introduction. So last talk was a talk of Alex Martsinkovsky, who was talking about the defect of an additive functor. This defect, the story, the history of the defect comes down to the works of Maurice Auslander, where he defined the defect, even not calling such a functor this way, for finitely presented functors. And after many years of using this concept without serious investigation of the subject, Alex Martsinkovsky and his student Jeremy Russell came to name that, let's call this functor a defect. And so what is this functor? This functor first was computed using presentations of finitely presented functors by short exact sequences. That was explained last time, and the big progress of the last year of my work of Alex Martsinkovsky and other people is that the defect was generalized to arbitrary functors from the category of lambda modulus to abelian groups, not just some finitely presented functors or some other subcategories. Right now on the screen you can see the formula. So the defect of a functor is defined as an abelian group of all natural transformations from this functor to the forgetful functor. This formula has a couple of imperfect sides. First of all, we are focusing only on functors that are acting on modules and giving values in abelian groups. Why this is a disadvantage, as we wish to have the defect, of course, for any additive functor that is acting from pre-additive, additive, or abelian category, not just from lambda modules. On the other side, very nice formula on the right, a abelian group of natural transformations from functor to the from a given functor to a forgetful functor assumes that we have a forgetful functor, so we have what to forget. Not in every situation we can forget something or go to some underlying structure, even if we have, will it be defect or not. And second of all, this was the first big disadvantage, or maybe first and second. And the last one is that this formula looks very appealing, and we wish to generalize it to a larger context. What if we are going from some usual category to category of sets, or if we are working in some
No, something happened with your mic, Alex. Something happened with your mic. No, we still don't hear you. Okay. No. You were good till a second ago. Yeah, still don't hear you.
Hello.
Yeah. Try. Sing so. Oh. Hold on, I'm going to press pause in the.
Okay, thank you. Let's continue.
Well, just one second. What's W? Small W.
The small w is the main hero, is the defect. The functor.
The defect is from the functor. Is something you get from the functor.
Yes, something I am getting from a functor. It is so good that it can be compared to a kernel of a linear transformation. Once we know the kernel of linear transformation, we can calculate the image. In certain sense, not completely in the same sense, it's so important for a functor. So for a functor, it's something very bad that if we can localize it, we can know everything good about the functor. So
I understand. Go ahead.
So this defect formula will be today generalized to other contexts. First of all, we will extend the notion of this defect W to any additive function. Second of all, I want to extend this notion not only to functors but also to profunctors, and I will tell you what is a profunctor and how profunctors are related to regular functors, but not to some profunctors, but also enriched profunctors. So if my original context was related to the category of abelian groups, now it will be related to any base of enrichment. And the last point that I will try to cover in my talk will be the application of the defect. So how this notion is connected with other very important ideas and dualities in category theory. Okay, but all this is just the outline, and now let's go. Oh yes, and before we will go, I wanted to tell you about the structure. So the structure of the talk and all the not only of the talk but also of all the notions that are involved today is the following. On the top we have a so-called Tensor-Hom-Cotensor situation that I will explain you in a minute what it is. Then for this Tensor-Hom-Cotensor situation that can be thought as triple of adjunctions, two covariant, one contravariant adjunction that connects three bifunctors. We can distinguish a class of Tensor-Hom-Cotensor situations for so-called weighted colimits. Weighted colimits are generalizations of regular limits, colimits that we know from category theory, but to bigger context, to enriched context, and not only to enriched, also in set in context of ordinary categories, we can also define weighted colimits. And from Tensor-Hom-Cotensor situations for weighted colimits, we can define Tensor-Hom-Cotensor situation for profunctors. But on the other side, we can define the notion of defect. And then both the THC for profunctors and defects give us a lot of information and we can derive from them very important things such as Isbell duality and generalized satellites. If I wish, if I had enough space here on the screen, I will draw you the whole tree of the notions that can be derived from the defect. But thankfully or unfortunately, the screen is too little and my desire is too big. But today I will try to cover at least very, very little part of it. But still, I hope it will give you a flavor how important and how wonderful it is, the defect.
Where do con extensions fit in here? Where, if you were just to put that in?
Con extensions are defects of certain profunctors. Well, once you will see the last slide on the last slide today, even if I will need to speed up at the end, the last slide, I think I need to show you. This result will cover all your questions. I hope completely all. Why it is important. Okay, so right now let's go to the part which is called conventions. So I will want to set up some things that will be used frequently. First of all, I will be working frequently with a closed symmetric monoidal category, which is bicomplete. Such categories I will call Cosmos. This name is attributed to Binabu from some paper published or unpublished. Yes.
You say the closed symmetric monoidal category is
Right.
bicomplete.
Which is bicomplete?
Yeah. So in particular, it's complete with respect to a product, or are you using the tensor as the monoidal product as a product?
It is complete with respect to usual product. So it's complete as a just category. So it has two structures, just regular structure of an ordinary category, and it is complete and co-complete in the regular sense. And also it has a monoidal structure in it. This monoidal structure is symmetric and is closed. So every symmetric monoidal category can be complete or not complete, co-complete or not complete. It depends on the category. But I'm choosing only the categories which are bicomplete among a symmetric monoidal category, closed symmetric monoidal category. Did I answer your question?
Yeah, it did. Thank you.
You're welcome. Well, I said Cosmos, but I never said any example of Cosmos. Well, the list of my favorite examples of the Cosmos are Cosmoi are sets, category of sets, category of abelian group, category of simplicial sets, category of small categories, category of convenient topological spaces, for instance, compactly generated weakly Hausdorff spaces as perfect setting for doing topology. Category just with two elements, 0 and 1, and one non-trivial arrow from 0 to 1. Maybe I can say
all these have the monoidal product is the Cartesian product.
Some of them have Cartesian products, some of them do not have Cartesian products. For instance, Cartesian product in abelian groups is a direct sum, but we are using tensor product tensor product as a monoidal operation. Yes, Cosmoi is a plural for cosmoses. Well, for me, it's more natural to say cosmoses, but usually in literature it's at Cosmoi. Sets, small categories. Well, who else? Simplicial sets. They have this Cartesian structure, but it don't need to be Cartesian structure. So I am considering the most general situation possible. Enriched, I will be working with an enriched category. So who are enriched categories? They are categories where home between A and B, objects A and B, are not just a set, but has additional structure. They are objects of other categories. I don't want to go deeply in this details, but you can think for convenience that they are abelian groups. For instance, your functor between enriched categories are preserving some of homomorphisms and so on. So if you want, you can skip everywhere letter V, and you will obtain just regular set enriched setting. So it's the setting of ordinary categories. But for people who are interested in other realms, for other cosmoi, I will write usually V. Also, I will be using frequently notation of superscript and subscript for bifunctors that are landing in some category C. So I will be putting a superscript for a contravariant argument and subscript for covariant argument. Since I will be working with different categories, my Yoneda embeddings need to have some relation to the category which they will be embedding. So covariant and contravariant Yoneda embeddings are right now displayed how they will be denoted. So it's the name of category with Yena, and Yena is at the spot where the argument will be put. Okay, then we'll go to the next part. Next part is called THC, so Tensor-Hom-Cotensor situations. The motivational example is just regular Tensor-Hom adjunction for modules. Once we are taking home from tensor product of a abelian group with a module to another module, we can move either abelian group S, either lambda module A to the other part of the home, and we'll have Tensor-Hom adjunction. But honestly, we have two Tensor-Hom adjunctions. And if we will look closely between homes, we also have a contravariant adjunction. The last statement means that in second and third element in a red formula, we have two functors that are standing on a second position inside the home, and home in category of lambda modules and home in category of abelian groups are being adjoined, but contravariantly adjoined, not covariantly. Well, this is a good, well-known formula, and it can be generalized to bigger contexts, especially to a context where we again have we will have something similar to the pair of covariant and one contravariant adjunctions. So by Tensor-Hom-Cotensor situation, I will mean a sextuple of three categories. First category S will be as category of coefficients. Let's call it this way, as it was abelian groups in the example above. Categories A and B will be categories that we will be trying to pair with the middle bifunctor that is called home, is denoted by brackets. And category S is acting covariantly on category A with results in category B, and contravariantly on a category B with results in category A. So this triple of functors that you can see right now in the screen is these functors are called Tensor-Hom and Coten. And in order to be Tensor-Hom and Cotensor, not just triple of bifunctors, they need to satisfy an isomorphism below, very similar to the one that we had for abelian groups and lambda modules. So let's go to some examples that can help to imagine and understand what do I mean. If we have, since we have our category V being closed and symmetric, we can act on a category V by itself and pair it also with itself, and use our tensor or our monoidal operation on a symmetric monoidal category V as a tensor product. Adjoints to tensor product when we fix either of variables will, when we fix one of the, either of the variables will be internal home. That's why we need closed the structure. But also internal home is self-adjoint when we fix covariant argument. So it's contravariantly self-adjoint. Therefore, we obtain that every closed symmetric monoidal category generates Tensor-Hom-Cotensor situation. Another good example is a case of so-called bitensored category. So category where covariant home has left adjoint and contravariant home has right contravariant adjoint. The first one is denoted using tensor sign, and another one is denoted using cotensor sign. So the statement that category is bitensored just means that we have the following Tensor-Hom-Cotensor situation in example number 2. Again, I emphasize that our home is precisely the home of a category C, and two categories that we are trying to pair coincide. And the last example on this page is the one that we started with. It's acting on abelian groups on lambda modules. So in this case, we have tensor product over Z as a tensor. As a home, we have home between lambda modules, and home over Z, it's a cotensor. So once you are working not in over commutative rings but over associative rings, it's not true that contravariant home will be right self-adjoint. No, it will be self-adjoint to home over Z, and that's why home and cotensor should be different in general. Okay, so that was about Tensor-Hom-Cotensors. Now we are going to part 3, profunctors. So profunctor is a generalization of covariant and contravariant functors that land in our base category V. So profunctors are just bifunctors, where one argument, first contravariant argument comes from one category and covariant argument from another category. I will denote them with a slashed arrow from A to B. For about examples of profunctors, of course, identity profunctor given by home is so home is a bifunctor, and it's an identity, and it is called an identity profunctor for a reason that we will see below, and it goes from a category to itself. Another good example of profunctor is the following. If we have any functor from category A to category B, yes, I'm writing everywhere and emphasizing that my categories are enriched, functors are enriched, and so on. But in order to speak more simply, I will be omitting this enriched, the words about the enrichment. So just will be talking a little simpler. So once we have a functor from category A to category B, we can construct two profunctors. One profunctor comes from a home in category B, but in this home we are twisting the first argument with the functor f. Another comes when we are twisting in again home in category B, the second argument with the functor f. The first one, B superscript f, I did not write it here, but it's called co-representable profunctor, and the other one representable profunctor. So for any functor, I can immediately generate two profunctors, representable and co-representable. Another good example are classical extentor bifunctors. They are respect x is a profunctor from lambda modules to lambda modules, and yes, here we have of course a typo. How without typos? That Tor is a profunctor from opposite category of lambda modules to right lambda modules to left lambda modules. Why do I have here opposite? Because profunctor takes the domain with op sign and codomain without it. Since Tor is covariant on both arguments, I should put here op on the first argument. So these are just a few examples of profunctors. There are of course much more, but certain theorem, at least for set valued profunctor, states that every profunctor is a composition of representable and co-representable, or co-representable with representable. Both are equivalent formulations. So the profunctors in example number 2 are the main heroes that exist for profunctors. Before I will give you a formula for composition of profunctors, I need to recall some. Sorry, I have a. We have a question in the chat about that his ex-tormentor. Okay, that was a comment. So we have a comment about extentor in chat. We need ends and coends. Now, I am heavily using in my investigation so-called coend calculus. That is quite fashion and fancy thing nowadays, but it makes a lot of computations very simple, and I would say you can quickly derive from one result to another. You don't necessarily obtain so you obtain for instance, we have limit and canonical morphisms going out of the limit. When we are using coend calculus, we usually obtain the limit itself as an object, but not with all the wires that connects it with the base or with the sides of cone. Colimit gives us something similar as for colimits, coend, excuse me. So ends and coends are very convenient for dealing with categorical structures, some universal constructions, and so on. And in order to use them, I need to define them. And since I'm working in an enriched context, I decided to give a brief definition what is end and coend in the case of enriched functors. So first we are defining end of a bifunctor, actually even profunctor in our case, from category to itself. It's given by a certain object in our category V, so in our base category, that it comes as an equalizer of the diagram below. I'm not telling what are precisely the two arrows, T upper star, T lower star, but you can think of them as you are twisting with morphisms first or second argument in our bifunctor. So the equalizer of this diagram will be called an end. When we will consider similar diagram, but there we use, instead of products, coproducts, instead of internal home tensor product, we won't compute equalizer, but co-equalizer, we obtain a notion of a coend. In a certain way, I'm returning back to end. Ends are something as natural transformations, and coends are something as connected components of certain category. This can be thought in this way, or ends is a universal quantifier and coend is an existential quantifier. This things you can look up more yourself, but it's good to keep in mind that end is a universal quantifier and coend is an existential one. Since I defined them only for profunctors from category A to itself, now it's time to define for bifunctors that land in an arbitrary enriched category B. So in order to define coend of a of such bifunctor T with values in category B, it is necessary and sufficient to define all the ends for profunctors where we are composing our given bifunctor with a representable functor. So in order to find end or coend of an arbitrary functor, it's necessary and sufficient to find an end or coend of this functor composed with every representable profunctor. And if such object exists, then it is end or coend of your functor. Okay, now once we get formulas for ends and coends, I can define and say what's the composition of profunctors. Once I have two profunctors, one from category A to B, another from B to C, I define their composition that I write diagrammatically as P diamond Q as a coend. Under this coend, I am making a convolution of a covariant and contravariant common variable B of two profunctors. If you think about discrete categories, so imagine that all your categories are discrete, and you have, for instance, a category of abelian groups as underlying category. This will be a product of matrices. If you think about category V being category with two values, 0 and 1 non-trivial error, so it's category of truth, false truth category, then you can think about this coend as composition of two relations. So your profunctors become relations, and the product is a composition of two relations. Okay. And now I have a few remarks about profunctors. First, I said that they are composed diagrammatically, not in a functional order, but in opposite one. Second of all, their composition is associative only up to canonical isomorphism. And the same is true about unitality. Hom in a category is being an identity profunctor for composition. And natural transformations between two given profunctors are defined as natural transformations between corresponding bifunctors. Also, I will use notation of slashed brackets for V category of V profunctors from category A to category B. And now about profunctors, I want to conclude that all the structures that we were trying to define constitute a bicategory of V profunctors. In this bicategory, our 0 cells are small V categories, 1 cells are profunctors, 2 cells are natural transformations between these profunctors, and composition of 1 cell, so profunctors, is given by composition of profunctors, of course. Composition of natural transformations is a composition of 2 cells. And identity 1 cells are given by identity profunctors. You can think about this category as about category of all bimodules, where 0 cells are rings, 1 cells are bimodules between rings, and tensor product of bimodules gives you horizontal composition, so composition of 1 cells. And homomorphisms of bimodules are 2 cells. Yes. So, but it's not strict to category, as we have associativity that holds only anti-unitality up to canonical isomorphism. So we have only a bicategory. Now, some important one very important thing about internal properties of this category. This category of V profunctors possesses right Kan extensions and lifts. So once we have a diagram as this one, we can define right Kan lift and extension using formulas. So when we have two functors, we are trying to extend one with another, find Kan extension. We are then we are looking at the object of all natural transformations on their contravariant variable, because they are coming from the same category, category A. So there it's on contravariant spot. If you are trying to find right Kan lifting, you are looking for two functors that land in the same category. So they meet in category C. It's the right side of the diagram. And you are looking at the object of all natural transformations once you are changing covariant variables in these two profunctors. So category of the profunctors possesses both right CAN extensions and lifts. And we have formulas how to compute them. And once
you don't have any requirement on that S. Go back. You know, S doesn't have to be somehow surjective or something.
No, nothing. So R is not required to be injective and has to be surjective. So it's not something as projectivity or injectivity condition. No, nothing like this. It's really as CAN extension and CAN lifting as we have in ordinary categories. Once I said about CAN extension and lifting, and they are known to be adjoint to the composition, then of course it's necessary to tie them together because they are related to the same composition. And they relate in the following way. They determine Tensor-Hom-Cotensor situation. So CAN lifting and extension, right one, can be thought as a division on the right or a division on the left. And composition can be thought as a product. And together they constitute THC situation. So we can write this long adjunction that we will do many times during the talk later. And what is the next? Next is the so-called notion of triangle of profunctors. So once we have three profunctors that can be put in a triangle, not necessarily commuting, so nothing and nobody talks about their composition, we can derive from our Tensor-Hom-Cotensor situation three isomorphisms between three objects. That precisely we see in the definition of Tensor-Hom-Cotensor situation. So this formula will be used a lot in the second half of the talk. Well, before we will define the defect, today's talk is not a lecture in category theory, especially enriched one. It's about the defect, but we can go there directly. We need to say what is the weighted limit and co-limit. So I decided to give a brief introduction how and why weighted limits and co-limits exist and look in the ways that they look. And for this, I need to go a little in the definition of ordinary limits and co-limits. And I will do in the following manner. So once I have a small category, J, and any category C, then limit and co-limit functors can be defined using left and right adjoints to diagonal functor. By diagonal functor, I mean a functor whose values at every object are constant functors. So delta sub C is a constant functor with the value C. And once we will write the isomorphism formula for every adjunction, we will see precisely the definition of limit and co-limit that we used to define once when we were studying what are limits and co-limits. And in the last picture, in the previous slide, I have one thing that is a constant functor, and constant functor is something that is very closely tied and related to category of sets. Why? Because it can be factored as a composition of two functors, one functor to a trivial category, which is denoted as 0 in square brackets, and another one is the functor from the trivial category to category C. The last functor from trivial category to C also exists in an enriched context, but there is no direct analog for a functor from a category to a trivial category in an enriched setting. There are many reasons for that, and there are certain cases when it will be such functor. For instance, as if our Cosmos V has Cartesian structure and terminal object is a monoidal unit, then yes, we will have similar to this because of terminality of this unit. But otherwise, once we will write the definition of an enriched functor, we won't be able to write any functor, just any obvious functor from your given category to a trivial one. So we have a trouble. We can generalize the previous way directly and have enriched limits and colimits. So what we will do, we will look on the other side on this definition. Let's look at the functor of cones. So what is a functor of cones? Its values on fixed some fixed object C is a set of all cones with tip of a cone C, and the bottom of the cone is an image of our functor F. So natural transformations Xi that fill the square in a picture are elements of a cone, each such Xi. And together all they constitute all these cones a value of a cone functor on an object C. Here I wrote functor 1 from category J to category of Z for a singleton valued constant functor. So our functor of cones is natural transformations from a singleton valued constant functor to a certain other functor. The same situation is for cocones, but it's a little it has a little enhancement with ops, as we need to use contravariant representable functors on the right side of a square diagram. But again, cocones also constitute of natural transformations. But now I am using the notation. I'm writing functor 1 from category J opposite to category of Z. So this using such functor, we will get a functor of cocones. And now we will say we can redefine the notion of limit and colimit in the following way: that if cone or cocone functor is representable, then a representable object is said to be a limit or colimit. And here are the junctions for isomorphisms written in the other shape. Okay, once we have such definitions, then we can think in the following way. What if we will change functor 1? So in functor 1 right now is our burden. Our burden is that we do not have natural transformation, do not have functors from a given category to a trivial one, but it's now as a part, it's a part of functor 1. So what if we will change this one to something else, something nice or not nice? The answer is the following. Let's not think about anything nice, just change this functor 1 by something that we want. And the functor that will substitute 1 will be called weight. And this weight functor will form a shape of a top. Before we have a cone, we had a cone, and at the top of cone was one single point. Right now we will have a cylinder. It's a generalized notion of a cone. So cone is a cylinder with a degenerate top, and once we will replace our weight 1, we had before weight 1 with arbitrary weight, we will have a cylinder with some other top. So I decided to write two diagrams that substitute diagrams for functor 1 that were before. In the same way, I can define cones, cone and cocone functors, and if they are representable, I can define weighted limit and colimit. So weighted limit of a functor, one functor by another one. I also want to emphasize that weight, the functor which is weight, should land in our base category, not now in Z, but in category V. So once we have a pair of such pair of functors, we can find and if we can find an object that represents functor of cones, this object will be called weighted colimit. So definition here is purely coined from the definition from the above definition of weighted limit, and the same about colimit. But for colimit, I am weighting my functor with a contravariant function. Returning back, weighted limit is weighted by a covariant functor, and weighted colimit is weighted by a contravariant functor. Now, once my category C is V by tensored, it's for purposes to compute my ends and coends. So everything what I'm defining is usually expressed in using ends and coends, but I'm skipping this technical details. So if my category C is V by tensored, then I will have adjoints to my limit and colimit functors. Before, limit and colimit had a common adjoint, and this common adjoint was a constant functor. Now they differ. So we have a problem. We want our adjoint that weight adjoint for weighted colimits not to coincide, but to be somehow balanced. Here we see that one is given by tensor and another by cotensor, and how they're related we have no idea. So we want to make the situation a little more symmetric, and the solution is to use profunctors. So profunctors they symmetrize situation as the relations are in some way they're symmetrizing functions. So given that triangle, but now in this triangle we don't have three profunctors, we have one profunctor and two functors. It's just a diagram. It does not mean anything to commute or to compose or anything else. It's just a picture. Once we have such picture, we can define weighted limit and weighted colimit in a very similar way as we did before, but right now our weights are parametric. So once we have a weight that is a value of a profunctor with one fixed argument, we will have colimit or limit weighted one, also being dependent on the variables that we fixed in a profunctor. So making profunctor as a weight means that fixing one variable we will obtain covariant weights, fixing another variable we will obtain contravariant weights. So our limits and colimits become now not objects but functors with arguments from a category where we are fixing arguments in a profunctor and values again in a category C, not just merely objects of a category C. I decided to give you a few examples that will give you a little hint how ubiquitous are weighted limits and colimits. The first example is the set of natural transformations for two parallel functors, W and F. So in the case when weight is weight and functor are starting in one category, in the same category and landing both in the base category V. So in this case, weighted limit will be a set of natural transformations from W to F. Second example is that once we will take, instead of profunctor, our identity profunctor, we'll get Yoneda and co-Yoneda lemmas. Co-Yoneda lemmas not in the same sense that Alex Martsinkovsky was talking last time, or in the sense MacLean meant, but in the sense that we are changing ends by co-ends and changing cotensors by tensors. So that's also there is also some lemma that is called co-Yoneda lemma. You can find it just writing down what is weighted limit, weighted colimit in the bottom row. Example number 3: can extensions. Can extensions of given two functors, we can find And if we can find Ken extensions, then these Ken extensions can be computed using weighted limits and colimits. So remembering the slogan of MacLean that all concepts are Ken extensions, we can say that all concepts are weighted limits colimits, because they also govern Ken extensions. And the last example is about ends and coends. So once we have a bifunctor T from C op cross C to D, we can find weighted limit and colimit and its weighted limit when we consider C not as a profunctor but as a functor from a C op cross C to category V will be its end, and weighted colimit by the same functor, not as a profunctor, will be its coend. So the most important notions as natural transformations, Yoneda and co-Yoneda lemma, Ken extensions and coends, all can be given by weighted limits and colimits. And now it's time to look at the adjoints for weighted limits and colimits. Again, I am writing a triangle with one profunctor and two functors, and I will have very nice looking formula that colimit and limit are right now on the one level in the formula for isomorphisms. Of course, the last formula tells us that we have a Tensor-Hom-Cotensor situations. Again, we have two covariant, one right contravariant adjunction, and the statement is the following: if category C is V by tensor, then categories A and B are arbitrary. Then our tensoring is given by colimit, our cotensor is given by limit, and our internal home is just forming a profunctor out of two functors with common end. So from a cospan. Well, we have defined all the notions that we needed, and now we can jump directly to the defect. So if I will consider a triangle as I just had before, but a specific one where one of the categories is a trivial category, which is denoted by I, trivial enriched category. So we have trivial terminal category in ordinary category theory. It's a category with one object and a single morphism on it. We can enrich this category and obtain again a category with one object and whose object of endomorphisms equals monoidal unit. So this category is said to be a trivial and category in a category of enriched categories. So once we consider such diagram as we have right now, we can derive the following adjunction isomorphism. In this adjunction isomorphism, on the right, we have natural transformations from functor Q to a representable functor. Sorry, what do we have this time?
Let's aim for 10 more minutes.
Oh, very nice. Very nice. I hope I will be done. If not, I can ask for 3-4 more minutes and to finish.
Yeah.
Okay.
Go. It's very interesting. It's full. You've got every concept in the book. Okay, go.
Thanks. So on the right in the adjunction formula for the written triangle, we have a set of natural transformations from a functor Q. Well, it's a contravariant functor. Contravariant functor can be written as a profunctor from a category to a trivial one, just unwind the definition, to a representable profunctor, contravariant one. On the other side, once we will use the adjunction formula from the above, this one, the red formula, we'll find that we have a colimit of weighted by our profunctor Q of an identity functor. Well, this formula, of course, means that there is an adjunction. And the guy on the left, V, is precisely a co-limit of an identity functor weighted by a by a contravariant functor Q. And this formula gives us left adjoint to the covariant Yoneda embedding. This functor V is natural to call a covariant defect. So it is natural to call covariant because Yoneda embedding, this one is covariant, and we will call it the defect. Why? We'll see a little later how it's related to the defect of that Alex Martsinkovsky said last time. It's the defect about the defect that he was talking about is related to the defect of Maurice Auslander. For letters V and W that we will have now are attributed and related to Auslander works. A similar situation happens when we have cotensor category B and we consider such triangle. It's a quite trivial case, but this trivial case gives us another very important thing. On the left, we have natural transformations from a covariant functor on category B with values in category V to a covariant representable functor. So image of Yoneda embedding or value of the contravariant Yoneda embedding on the object B. Again, we have an adjunction, but in this case, a contravariant one. And we have that right contravariant adjoint to contravariant Yoneda embedding is some functor W that is given by limit. Limit of an identity functor weighted right now by covariant functor. So if B is V contender category, functor W that is written right now on the screen is called contravariant defect. Again, contravariant because Yoneda embedding, which it corresponds to, is contravariant, and defect because it's a defect. Now I want to define something more symmetric. Before I have V and W just for functors, I want to define them for profunctors. There is nothing really tricky in this case. I will the only thing that I need, it would be, if we will return to the first picture, to change category I in my triangle by category A, and profunctor and contravariant functor Q by just a random profunctor P. Sorry, not a random profunctor P, but by a representable by identity profunctor. Yes. Oh, no, by random profunctor P. Okay, so in this way we will get V and W being covariant and contravariant defects of a profunctor respectively. Again, they will be given by weighting co-limit of an identity functor. Now I want to define two pseudo functors that are called rep and co-rep. So rep or representable embedding is a pseudo functor given from a co-category of category of small v categories to category of profunctors, which is given on objects trivially, and on morphisms it's given by a representable profunctor. Right now I need to stop for a second and say that what is co-category? So opposite category, in opposite category we are changing the direction of one self. But once we will get to the realm of two categories, there are two ways to make some opposition. One way is to change the direction of two cells, or natural transformations we can think about it, and another is to change the way how one cells are going, and one cells can be thought as functors. but not changing the way of how natural transformation change. So once we'll get to two categories or bicategories, there are two directions, and each of the directions we can reverse. So the direction where one cells are reversed is called co, and where two cells are reversed is called op. Of course, co of op and op of co coincide. So rep embedding will act from V co of co-embedded. So co-category of small v categories to V-Prof functors, and another one, co-representable embedding, will go from opposite category, from opposite of category of small categories to category of Pro functors by co-representable embedding. I also gave a remark that I skipped on the previous page that tells us that representable embedding when we fix two objects, so our objects are categories, one is trivial, one is A, gives us back our covariant Yoneda embedding. And once we will do the same for co-representable embedding, we'll obtain contravariant Yoneda embedding. Well, now once we defined rep and corep, I can state the main theorem for the defect is that defect V is left adjoint to representable embedding, and defect W is right contravariantly adjoint to co-representable embedding. The first statement is true when category A is V-tensored, and the second statement is true when category B is V-cotensored. Since our rep and corep are faithful functors, full and faithful functors, we'll have that V of rep is isomorphic to an identity functor, and W of corep is isomorphic to an identity function too. Well, now let's revisit the situation that Alex Martsinkovsky told us is a situation about the defect of a functor with that acts from modulus to abelian groups. So when we will write W of such functor f, we should compute a weighted limit of an identity functor weighted by this functor. This is given by end. Under the end, we have a value of our weight on object P, cotensor with object B, but cotensors for category of lambda modules we defined in the beginning are given by cotensoring by Homs as abelian groups. So we will have end of Homs Z from f of B to B, but in order to put everything on the same board, we will write not just module B as a abelian group, but we will also apply their forgetful functor. So forgetful functor U of B is means that we'll consider module B as an abelian group. The last equality is actually a theorem that says that natural transformations from one functor to another can be given by can be described by n. Well, so comparing the first formula and the last one, we see that the defect of functor f is given by natural transformations from functor from this functor to a forgetful one. Well, that was all that I wanted to say about the defect, and now let's go to Isbell duality in the rest of the time. Well, we have been talking about the up to now profunctor triangles where we have two functors and one profunctor, and we were using and abusing so much Tensor-Hom-Cotensor situation for weighted limits and colimits. Now we'll do the same for Tensor-Hom-Cotensor situation for profunctors. But I want to consider the case where one of the categories, and right now intermediate category in this profunctor, so the category which is between two composable arrows, is a trivial one. From such profunctor, we obtain V natural isomorphisms, as you have right now on the screen. The left most part is not right now interesting to us, and from middle and the right one, we can derive that what? Okay, I have a typo in the middle. It should be ren sub f. Yes, that we have two functors and that are adjoint to each other, and we obtain right contravariant adjunction. I denote by upper star lower p and upper p lower star ren and enriched of a profunctor p respectively along the argument, and they form a pair of adjoint functors. They will be called upper and lower Isbell p duals respectively. Why such name arises? When we take p, our profunctor, as an identity profunctor, we obtain classical Isbell duality. So once we have such triangle, as you see right now in the middle of the screen, and two functors f and g, so f is contravariant, g is covariant, we get right contravariant adjunction between the category of preshifts and category of copreshifts. Functors upper star and lower star are the same as before. I'm just skipping the argument where the profunctor stays, as I'm taking the identity profunctor. In classical Isbell duality, left functor, so upper star, is usually written as curly O as global sections, and the right one as spec. That's because this O spec duality from algebraic geometry is a partial case of this classical Isbell duality. Among the other examples of Isbell duality are Stone duality, Gelfand duality, and many others. Well, even these couple dualities already say that Isbell duality is quite general. Oh yes, I forgot Tanaka or Tanaka, I don't know how to pronounce duality. Also is example of Isbell one. Some people claim that Isbell duality is the mother of all dualities, and I won't contradict this statement. Also for the reason that you will see in a few seconds. Auslander-Gruson-Jensen duality from representation theory. So if I consider such triangle of profunctors, where by the in role of profunctor I'm taking tensor over a ring lambda, then I obtain a natural isomorphisms between that gives us a junction between two functors, d sub r and d sub a, that are given by formula that their values and functors are natural transformation from these functors to tensoring with certain module, left or right respectively. These functors are called Auslander-Gruson-Jensen functors. They form right contravariantly adjoint pair, so they give us right contravariant adjunction between category of functors on right lambda modules and on the left lambda modules. Again, I want to go back and to say that this left and right lambda modules I managed to write in this way using Profactors. So here you don't have any op signs inside or outside. You just have lambda right lambda modules and left lambda modules. Well, since I did said something about the defect of a profunctor, not just functor, it's the same I should do for Isbell duals. So when I am changing my trivial category I to category B, and considering the case when the profunctor that was in the middle before is again an identity profunctor A, I obtain the isomorphism between Ren and Rift. And the arguments in Ren and Rift are the arguments along which we are trying to lift or extend. So functors, upper and lower, stars for profunctors right now, again, will be called Isbell, upper and lower Isbell duals respectively, but now of a profunctor. And again, we obtain right contravariant adjunction. What's interesting about this contravariant adjunction? Before, it was before category of preshifts and category of copreshifts. Right now, it's between two profunctor categories. So both Isbell duals change the way profunctor goes, either from the left to the right, or from the right to the left. What else is interesting in this formula? We can apply both upper and lower Isbells twice, thrice, how many times we want, not interchanging them. Before, once we were talking about the contravariant classical Isbell adjunction, going from preshifts, we get in copreshifts, from copreshifts we will go to preshifts and vice versa. So every time we need to apply either upper, either lower star, but we can't apply 2 times upper star or 2 times lower star. Right now we can. So this situation covers also some, even now, undefined situation, but which can be very, very interesting and appealing. So this left and right, sorry, upper and lower Isbell duals change the direction of profunctor. And Isbell duality follows when we take category B equal trivial category I. Well, let's wrap up the things and join defect and duals. So the statement is the following, that upper Isbell dual factors through the covariant defect, factors in the way that you see now. So the upper dual of a functor P is given by a representable co-representable profunctor, and co-representing functor is precisely the defect. Furthermore, once you will apply lower star, can you see me? Hello?
No, I can't see you. We can't see you, but we're reading. Go on.
Can you hear me?
We hear you perfectly.
Okay, good. I have no idea why I have disappeared.
Okay.
So, well, the main is you can hear me. So if we will apply first upper and lower dual, we'll lift down upper our representing functor, and applying third time we will return, of course, to the original one. So that's why we have duality. So left, right, left equal left, and similar to the right, left, right equal right. So this the same thing as we have for annihilators in rings. Yes, the second theorem is about that lower Isbell dual factors through the W defect in a mentioned way. Well, I would say that it would be all for today, but no, I have one more slide, and I wanted to show it to you. So again, we will return to the triangle of weighted limit and colimit. Once we have category C being bi-tensored, we can obtain very easily that weighted limit and colimit, weighted by a profunctor, are given by defect of a certain profunctor. So if every concept is a con-extension, and con-extensions are given by colimits, then I will say that every concept is a defect of a certain profunctor. Which profunctor? That's another story. Thank you for your attention.
Nice, thank you, thank you. I have a question.
Yes.
But let's ask anybody else. Anybody else want to ask a question first? All right. Somebody asked in the chat. Ray, shut your thing in the chat. Are you familiar with the literature on Isbell and conic adjunctions in quantiloid enriched categories? It seems very similar flavor to the topics you have been discussing. Categories enriched over quantiloid Isbell adjunction and conjunction. Would be interesting to hear how your work relates to this.
Well, I don't know what is quantiloid right now. It was already a big piece to swallow, but thank you very much for such link. Yes, I already opened it and I will save it. Thank you so much. I don't know anything about that, so or Isbell adjunction or Khan adjunction. What is precisely? Yeah, but thank you. I will take a look.
I didn't understand this Auslander Gruson-Jensen duality. It's a type of Isbell duality.
Yes, it's also a type of Isbell duality.
And so is it somehow the ultimate one or?
So the ultimate one is Isbell.
I understand. Okay, and what would be if there was a trivial defect? In other words, what would be an Isbell duality that didn't have a defect, or the defect would be trivial? What would that signify?
So the defect, let's say this way: if we have a representable functor, the defect of it is representing object. If we have a representable functor and we will take a dual of it, we will just swap the representing object and argument. So trivial things for duality, or I would say center of duality, it's called center of duality or nucleus of profunctor, many different names. Are functors that are not changeable or where we just swap it. Among them are representable functors. Among them will be representable profunctors. So representable profunctor will become co-representable, and co-representable will become representable. About other profunctors, I can't say anything right now. Alex Martsinkovsky asks me frequently, what does it mean for defect to vanish? Because the defect of a functor, of an additive functor, can vanish. It can be just zero module. It's true for in a case of modules or abelian or case of categories enriched in abelian groups, or we have where abelian categories and so on. In general, I have right now no idea what does it mean for defect to vanish or something like that. I only can say that representable functors and profunctors and co-representable ones lie in the center. Yes, and one other thing I wanted to emphasize and say before I forgot it, that this defect thing gives us the best approximation for our presheaf by a representable presheaf, or for a co-presheaf by a co-representable presheaf. It's the best approximation.
Very good. Any more questions?
So, Austin, you mentioned that the presentation was full, but I'll venture to say it was also a faithful representation of the material as well.
Yes, very good, very good. Anyways, thank you, Alex. Thank you very much. Very interesting. I just want to finish off. Next week is Gershom is speaking. Is the last talk of the semester, and you're all invited back. Anyways, again, thank you, so Alex, and
thank you.
Good luck and stay safe.
I do. Thank you so much for inviting me. It was an honor to present my topics at your seminar. I hope that maybe one day everyone will use a piece of it somewhere. The defects are everywhere.
Okay, and one day we're going to get back to in-person meetings, and you're going to come give another talk.
Thank you. Thank you.
And you're going to tell us what happens when, when a defect vanishes, or more importantly, I mean, there must be a partial order of all defects in some sense. So, what does it mean when one defect is worse than the other?
No, the defects are both good. So it's as your left and right hand. If you will cut one of the hands, you will, you'll become a little disabled. So we need both defects. That's the moral of the story, and they are different.
Very good. Okay, thank you very much.
Thank you.